So let's continue on with our discussion of components. So we're going to take the Jack Sparrow example and do 4 others on our own from diagrams. Again, being in degree mode on your calculator, very, very important that you work through every little detail on this so you find out what you get or don't get. This will make sense when you do it enough. You just got to follow a process and not just wing it. You have to understand when I give you an angle and say south of east or north of west, where that is, and then you're just basically taking a vector, which is a hypotenuse of a right triangle, and just building a right triangle around it. And make sure you put arrows on that. That's a common mistake. So I have 4 vectors here, and I've given you information what you want, and I want you to fill out this table where you find the horizontal component and the vertical component. I'll do the first 2 with you, and then I want you to do C and D on your own before I give you the answers. So let's look at A. I have some vector representing the velocity. So remember, these arrows can represent any vector: velocity, displacement, acceleration. We'll eventually learn force. So don't get in your head it's just a distance or a displacement. And it's 90 degrees east. So it's just this way, to the right. So I want to know how much of that is horizontal and how much of that is vertical. Well, if I look at that and I ask you what direction is that pointing, it's to the east, it's all horizontal. So I don't have to do any trig for that. I mean, that value is 10, right? That's just going to be 10 meters per second. So now I ask you for vertical. Well, how would you make a right triangle that has a vertical of this? If I try to draw something vertical, I can't do it. There's nothing about that vector that is up or down. It's all flat. So the vertical is simply 0. There's none of it is moving up or down. So I want you to recognize that when we can have vectors that have just one component. The next one you can see is pointing down and to the right. So there is a down component, vertical, and there is a rightward component. We just want to find that. So in order to do this, we want to make a right triangle. Now don't draw anything yet. So I want you to understand there's 2 ways I could make a right triangle from this hypotenuse. I could go down, put an arrow, to the right, put an arrow. Or I could go right and then a down. So one fits the information better than the other. So this is how you work it out. I look at the information given. I say it's 40 degrees south of east. So this vector B is 24. You know that's the length, the magnitude. So how do I draw 40 degrees south of east? Well, of east means we're referencing it from the east vector. So I've drawn this little dashed line. That's east, the vector. So I want to go south of it. And so there's my 40 degrees. So in other words, I want to build a right triangle that has that 40 degrees within it. If I were to do this, the 40 degrees wouldn't be part of that, so I'm not going to go that route. That's how I tell how to draw the triangle. So the beginning of my 24 meter vector is here. I want to start here, end up there, and make a right triangle. That's all you have to do. You start at the beginning of the vector, go to the end of the vector, and make a right triangle where the angle in question is encompassed by that triangle. So basically I go to the right, and please put an arrow. I put an arrow. I've indicated I've gone that way. If you draw just legs without arrows, you're going to lose points. Then I'm going to turn down, and I put an arrow to indicate there's that. So I'm going to call this BX, and I'm going to call this BY. Right? X is for horizontal, Y is for vertical. Now I just got to find those values. Right above you, you should see that in your reference tables, there's a nice little, actually I'm not going to do it that way because I want us to work out the SOHCAHTOA ourselves. So let's try to find BX and BY. So here is my angle, Y. So ask yourself which component is adjacent, which is opposite. So it's pretty clear that X is adjacent. So I'm going to say, okay, cosine of 40 equals adjacent over hypotenuse, and my hypotenuse is 24. And then for the Y component, I can say sine of 40 equals the opposite over the hypotenuse. And then I can solve for BX and BY. So again, make sure you're in degree mode. And so your BX is going to be 24 cosine of 40. So if I work that out, I get 15.4. And if I do 24 sine, then I get, whoops, I got that reversed. Silly me. So 24 cosine is 18.4, and 24 sine of 40 is 15.4. And in this case, they're both meters. So these represent displacement vectors. Alrighty, please try to do C and D. So label the vector that represents that acceleration, put the angle in the proper place relative to the vector, then draw your components, then find the value of each component. Okay, so pause here. So here are the answers. I look at the chart, and I'm going to walk you through to make sure, to show you how the process works if you have something different. Or even if you have the right answer, make sure you have it set up, because I need to see all this work. So for in C, we want 20 degrees west of south. So that's that little angle right here. So the beginning of my vector is here, so I'm going to go south, follow that arrow, and then go west. Notice I put arrowheads on it to indicate the directions I've gone. And this is consistent with the idea of down and to the left gives me a vector that's down and to the left. Notice that my y vector is much larger than my z or x vector, so I should get a value that reflects that. So this is where the SOHCAHTOA, where we can't necessarily use the reference tables here. The x component is opposite the angle, so I have to use a sine. And the y component is adjacent to the angle, so that's why I had to use cosine. So I've set up the trig function there, I plugged in the numbers, and I got 47, or about 48 for the x component, and 131 for the y. So the y component is much larger than the x, is what I expect. D, very similar. 75 degrees north of west, so I drew the west line, so we're going north of it, so there's my angle, so I build my triangle around it. So I go west, then north, I put arrowheads on them, and then I notice that my x component is adjacent to the angle, so I use cosine. My y component is opposite, so I use sine. And notice that my sine, my vertical one, seems to be much larger than my horizontal one, and the trig bears that out. Okay, so we will have a little bit more practice in class, and then when you come to class, if we haven't done so already, I'm going to show you how to do the same thing graphically using a protractor and ruler.